a little overview of what's going to be the program tomorrow morning, and he's going to talk about UV morphology of star-forming galaxies at redshift 6.
So yeah, at least from the observational viewpoint. So it's been said already, it will be debated much more tomorrow, but our general ideas about how baryons populate dark matter halos and then settle there and form stars is basically, I know what's going on here. What goes under the name of the tidal torque theory. This nice cartoon comes from a recent paper by Mark Damovich and Avishai's group, in which is the idea is put down that the baryons enters, acquire a fraction of the dark matter halos, settles inside, reach very deep inside the virial radius, and then there is an area where, in fact, the star formation occurs in which most of the details are murky and the troubles come. And there are models that predict what happens in there. But the basic idea is that the baryon settles on a rotationally supported disk where they form stars and do other things. A prediction of the theory in particular is that the distribution function of the specific angular momentum and the size of the disk, which is proportional to the specific angular momentum, is a log normal function. So the question is, do we see this general feature? This is a very general prediction, right? Do we see these general features in the data? I'd like to point out this recent and quite nice work by a team of Japanese led by Shibuya. Paper is now published on APJ supplement. And these guys have studied just shy of 200,000 galaxies from the whole Hubble archive. They have selected star-forming galaxies in various ways, but at high redshifts, a redshift larger than about 2, primarily as Lyman Bray galaxies from the UV colors, various flavors of selection. And they've measured their morphological parameters. And what they find here is a measure of the average RE, half-life radius of the Sursich function, the Sursich index with their dispersion, and also the projected the density of star formations in various redshift bins. They reach out all the way to redshift 6, even higher than 6, in fact. But redshift higher than 6, the statistics is spottier, of course. And what they find is they do find, there's also they do find, for example, that the average evolution is what is expected from the tidal torque theories in the case of mass-selected halos or rotational velocity selected halos. We can't select by mass or by rotational velocity, so the selection is somewhere in between. But the data fit nicely, are bracketed by these two cases. They also do find a key, one of the features of the theory, that the distribution function of sizes in the various redshift bins is something that strongly resembles a log normal theory, which would suggest that we more or less get at least the fundamental features of the theory of how baryons accrete on dark matter halo right. But at high redshift, we also know that very often we encounter galaxies that are very compact with very high stellar density, or at least we think the stellar density is very high, certainly are very compact. In fact, a redshift larger than roughly 1.5, all passive, a big fraction, the majority of passive massive galaxies or low star formation galaxies are nearly all compact, okay? So they should be the first system to passivize. And there are comparable numbers of similar star-forming galaxies. Comparable means of the same order of magnitude. Maybe it could be a third less or half less, but similar number of compact and massive star-forming galaxies. Are they also disks, in particular compact disks? Somebody actually suggested this. Van der Velde and collaborators, Hans-Walter Rix and others suggested this, based primarily on the distribution function of axial ratios. Isn't a great constrained, but they suggested that these, in fact, are compact disks. But the questions we still don't know is whether these very compact systems are consistent with the tidal torque theory or not, or they are evidence of yet unidentified formation mechanisms. And if they are, a very good question to answer is, do all galaxies undergo a compact phase as they evolve or not? So let's see what clues from the observations we have. Regardless, though, the significance of these objects goes beyond the context of the evolution of quiescent galaxies themselves, as is often been. It really goes down to the physics of baryon accretions and transformations of the gas into stars and so forth. I took this picture from a recent paper by Peter van Dokkum, where it shows colors and morphology of these compact objects, both star-forming and passives. Here is the RE fit that he does, and other teams find similar numbers and so forth. So, there is some dynamical information. We don't know whether these systems are mostly velocity supported or mostly rotation supported. There is some dynamical information. I took this picture because I'm one of the co-authors from a not so recent anymore paper by another at all, but there are other very similar studies that reach essentially the same conclusion. What you see here, for example, is the Sloan velocity dispersions versus dynamical mass relationships, and these points are high redshift galaxies. Basically, what this plot tells you is that, yes, they are massive, and yes, they are compact, and therefore we see the corresponding velocity dispersions. Or, I should say, kinematical indicators, whether it's velocity dispersion or rotations, we don't really know. Okay, so there is no evidence for or against rotation. But the dynamics is roughly consistent with, these objects being massive and compact. Galaxies do passivize, and we do know that the way they get passive has to do with the environment and also with intrinsic properties in ways that we still don't fully understand. But something that seems well established is that a high redshift, at any redshifts, quenched galaxies are very often compact in that they have a high Sircich index. Okay, this is up to redshift 1.5 in the recent studies, but in fact, as I shall see in a second, this holds at even higher redshift. This is from a couple of papers I published with Paolo Casada when he was with me at UMass. What you see here is the volume density of passive galaxies sliced, what shall I do? Sliced in 3 bins of compactness, what we call ultra-compact in red, compact and normal, where the definition of compact, ultra-compact and normal is done in relation to the mass size relation, a redshift 0, here at Sloan data in gray, and minus 1 sigma below the mass size relationship of redshift 0 and 1.7 times below. So these are compact, these are ultra-compact, and so forth. What you see here is that the most compact galaxies, essentially, dominate over less compact galaxies, high redshifts. Then they reach a peak of popularity, and they seem to decline. Although I should point out that this is a strictly lower limit, because we're not really sure we have done a full census of very compact gases in the local universe. They're actually really compact. In surveys like Sloan, it wouldn't be that hard to actually mistake them for G stars or K stars. And there are papers in which they claim they've identified in the point source catalog of Sloan many more compact galaxies, in fact. And so this point could be revised upward. But we don't really know yet. Oops. Now, if it is true that the first objects that get passive are the most compact ones, we should see this. We should see a trace in the stellar ages. So with Christina Williams, who's now, when we started this project when she was a student with me, now she's a postdoc in Tucson, but the paper is not yet ready. We're still working on it. We studied this at redshift 1, although I have to say by means of optical spectroscopy, but there are similar studies done by people at Caltech, Sirio Belli and Richard Ellis at Redshift 2 using near-infrared spectroscopy with MOSFIRE. Basically, we sliced galaxies in terms of compactness, normal and compact and also ultra-compact galaxies. And we studied indicators of stellar age, the D4000 break and the equivalent to it of H delta, okay? Before I go ahead and show you the result, let's have a look at the spectra of passive galaxies. They are classified passive based on the UVJ diagram. As you can see, there is some oxygen 2 emission. Compact galaxies in red have weaker emission. Normal passive galaxies have stronger emission. But you also see large Balmer 4,000 Armstrong breaks, deep Balmer absorption feature, calcium H and K, G-band, the typical features of post-starburst galaxies. What is this? Let me show you also another key piece of evidence, which is the fact that the frequency, now this plot seems complicated, let's focus on this plot up here. The frequency of oxygen 2 emission strongly depends on compactness. In particular, oxygen 2 emission is very rare in ultra-compact galaxies. It's much more common in normal passive galaxies. What you see here are Monte Carlo realizations of assuming the oxygen 2 can or cannot happen with equal probability. If we extract a random samples like the ones we have stacked together, how many times we do find oxygen 2 in the ultra-compact, and how many times we find it in the normal galaxies. So this is if oxygen 2 can be found with half 50% probability and 50% cannot be found. Well, this is what we observed. So essentially, you put very strong constraint on the fact that oxygen 2 is much, much rarer in ultra-compact galaxies than it is in normal passive galaxies. So what is this oxygen 2? Well, both Belli and us speculated this is probably some liner activity. And we think this is not a quenching agent. This is probably a tracer of residual gas accretion. And the gas accretion is smaller in the more compact objects, okay? Presumably, it doesn't have to be an AGN. In fact, I will show you in the candles field that is probably not an AGN, okay? Let me show you this right away, in fact. These are Chandra stacks. These are like 40, the stacks of 40, 50 Chandra 4 megasecond images, so the number of megaseconds that enter these stacks is ginormous, okay? And what you find here, for example, ultra-compact galaxies have they have detections in the soft band, they have an upper limit in the hard band at the level of liner luminosities. So we don't really know what powers up liners. It could be star formation, it could be an AGN nucleus. Regardless, if we are right that these are tracers of residual accretion into the center of the galaxies of gas, that is still powering this liner, the more compact a galaxy is, the less able is to do this.
Mauro, are you talking only about compact quiescent galaxies right now?
Yeah, right now, yes. So what is so let's have a better look at the morphology of these compact, quiescent galaxies. ET stands for early type. Maybe I shouldn't call them early type because these are not ellipticals. We don't know at least, but passive galaxies. If you stack a huge number here, there is forgot the exact number, but there's all of them in good south. They are really compact. They're really, really compact. You can see the diffraction spikes a little bit, right? They are nicely fit by a Sursic profile. This is not a surprise. In fact, there's a paper, I will give you the reference in a second, that, oh my gosh, that any radial profile, if you decompose it in Taylor series, the first order of the expansion is a Sursic function. So when you have only a few resolution elements into the galaxies, it's not surprising that Sursic is good. But the Sursic parameters are interesting. It's very, very compact, right? And with n, which is bigger than a disk, but smaller than a divocular, violently relaxed structure. The big question is, are these systems intrinsically different from local ones? What you see here is the best fit profiles and the real data of the stack I just showed you, calibrated in masses instead of light, plotted against Kormendy's local ellipticals, a sample of Caspi galaxies. Hubble runs out of steam, we can't resolve the inner parts of the galaxy. It just don't have the resolution. This bending over is artificial, right? But if the extrapolation is correct, the high redshift galaxies are as dense as the densest galaxies you find in the local universe. And so they can be up to 2 orders of magnitude denser than less cuspy galaxies. But they lack the extended envelope out here. They lack this. They lack what makes the Vaucouleur profile, essentially. In fact, what is the meaning of the, I don't have much time, but what is the meaning of the Sircich index? So take a disk. A disk is, you know, not very hard in the center, doesn't have an extended halo. If you increase n, you increase the halo, and you make the core bigger. Also bear in mind that very seldom galaxies are described by only one Sircich function, implying that you can have a cuspy center, an extended halo, and you need to increase n to provide a fit, okay? Let me skip this. So there is no evidence of this. How do we form these things? How do we form these objects? People have proposed that you can form them by binary merging, very wet merging. Well, the bottom line is that it won't work. If you do, this is from a relatively old paper in which simulations here in gray, this is the Sircich versus RE plane, are compared with data. What happens here, depending on which gas fraction you adopt, either the system is too big, right? Or even if you get it small, it has such an extended, violently relaxed halo that it drives the Sircich index to impossibly high values. The observed points you see here are ultra-compact and compact ellipticals and star-forming galaxies that we believe might be possible progenitors. And the diamonds here are the stacks that I have done to illustrate the average behavior. Let me just say that binary merging doesn't work, and there are other lines of evidence that show that, and I'm going to fly over this. So what can form these objects? And Guillermo will show more about this, but I want to show this plot from the same paper of Van Dokkum I cited earlier, in which he also plots, together with the quiescent compact galaxy evolution as a function of redshift. This is essentially the Cassata plot repeated here. Peter also shows the evolution of star-forming compact star-forming galaxies, which also show a similar behavior, although delayed, suggesting that one can be the progenitors to the other. And what is also interesting is that the population of massive compact star-forming galaxies increases with decreasing redshift, implying that they get formed, right, somehow. So galaxies, compact galaxies increase in popularity, reach a peak, and then decline as well, star-forming ones. The plot here shows how we have selected candidates, progenitors of quiescent galaxies among star-forming galaxies. This is our circularized half-light radius versus stellar mass. Essentially, you choose candidates among compact star-forming galaxies. I skipped the details. And I also skipped some of the properties because I have no time. I want to move to the last thing I wanted to present new here, which is the earlier phases of star formation. So, is what Peter finds true, that massive compact galaxies ramp up in popularity in the universe somehow? Can we see the early phases of creation of these galaxies? So to investigate this, we've been studying galaxies that have spectroscopically confirmed redshift. Not that we don't trust photometric redshifts or color selection, it's just that we don't want complications. We want to be absolutely sure what we see. Right? In 2 redshift bins, separated by about 200 mega years, 300 mega years, something like that. This redshift bin, 5 to 6 essentially, and 6.2 to 7.2. All these are in candles. The spectra come courtesy of the AstroDeep collaboration spectroscopy program led by Laura Penterici in Rome. I was sabbaticing there. And what I offer here are stacks, okay? Are stacks of these images. Now, what is the meaning of stacking images? Right? So stacks includes images with different size and profile. Very likely the size and the surface index you find have nothing to do with the distribution function of the individual ones. But the stacks tells you if you have low surface brightness outer things and the relative balance between the outer regions with the central part. That tells you. They're also very useful to probe the onset of color gradients and in a comparative way how things change if the samples are representative. I wanted just to show you panoramics of these galaxies. Let's skip it. Maybe in the discussion we can go over. And let me show you the results. The results is that these are the two stacks. Mean redshift 5.2, mean redshift 6.7. Here they are. Beautiful surface fit, right? Subtraction is very nice. Leaves no residual. Look at the surface index here. They are diskish of high redshift, low redshift. So I inverted them. They are diskier at high redshifts, and these two panels are inverted. Apologies for this. And they are bigger at lower redshifts. I don't know how I did that, but I did it. Okay. The bottom line is that in this lapse of cosmic time, the sizes of the galaxies grow marginally. Very marginally. It's not a big deal. In fact, they seem to shrink a little bit. Okay? The central part. But it's the surface index that gets larger, from M1.7 to 2.4. Are we looking here at the growth of the outer halo or not? And then what is very interesting is that the UV color gradient develops. I have no idea why now all of a sudden I lost the figure. In the discussion I will show you because it's nice. Essentially what happens is that the stack at lower redshifts has a color gradient that is not observed at higher redshifts. I don't know why this happens. Either with passing cosmic time, the outer regions get dustier. It could be that the winds are pushing dust. Or maybe somehow, if the same stellar populations, if stars get scattered away from the center to the outskirts, the only one that reach out are smaller mass stars because the bigger one die as supernova during the trip, and so you get rather UV colors. And I put here a teaser for Avishai. We're seeing the onset of compaction. Just to tease you because I like that. Sorry for being over time. The conclusion. So basically, I read the conclusion already. Most star-forming galaxies of all epochs are actually consistent with being disks. Okay, the TTT predictions in its most general form seem to support. But the nature of the massive compact galaxies, whether passive or star-forming, remains unclear. They seem to show it's unlikely that they are mergers, as I said, binary mergers, although some might be. Compactness seems to be related with the physics of quenching, of mass quenching. This seems robust, although we haven't understood the physics behind that yet. I haven't discussed this, so I won't read it. I tell you, even if I didn't show you, there is no obvious evidence of AGN feedback being behind this. It's not obvious. If there is it's not clear. The population of compact galaxies, both star-forming and passive, seems to grow with time and then disappear. It's possibly that there is possible direct evidence that early star formation of galaxies evolved to become more compact with time. Better samples, which are collecting, should be able to answer that question. Thanks.
Thank you. We have time for a couple of quick questions before we start the discussion.
Color gradients. I don't know why these appear. You ask me the questions, I find the color gradients.
So, Mauro, I am confused by the first part of your talk and puzzled by the second. Yes. So I now read on the summary that you do find that the most that the compact galaxies are older than the larger one.
The more compact ones have older stars.
Older.
Yes.
From then on, the question, as far as I can read in this debate, is not whether the compact population increases in relative numbers as redshift gets higher. Everybody agrees on that, is why. And as far as I can see, the two big competing scenarios would be the fact that the compact are made compact early on because the universe is denser, and versus I made the compact at any time and I actually turn hollow. And I confess I didn't understand in what you showed how these observations are going to break this degeneracy. So as far as I can see, they're both still, despite what you show, perfectly valid interpretations. Can you comment?
I'm not sure I understood the degeneracy question, but the reason why they are so compact might have to do with the fact that the density of the universe was higher. Yeah, probably. There must be something very dissipative that brings gas in there.
But isn't it this, the entire debate which is taking place at the moment, what is called progenitor bias versus the idea that you accrete the halos through the minor mergers? And
Marcella, not all galaxies are so compact, right? In fact, the ones that are so compact among the star formers are a minority. They are a majority among the quenched one, that's true. But among the ones that star forming, not only a minority are so compact.
But of course,
so,
this you can show very easily that if you have star formation, you just, you can just literally do the analytic calculations that you shrink the system as you quench down your system. So anyway, this may be for discussion.
I'm simply showing what I observe with not preconceived ideas about how they should be forming, right? I also ask the questions, can I identify the parents? Sure, I do that, but...
All right. Any other question for Mauro? Well, if not, let's thank him again. And actually all the speakers of this session as well.
Refraction of the dark matter halos settles inside, reached very deep inside the radius, and then there is an area where, in fact, the star formation occurs in which most of the details are murky, and the troubles come. And there are models that predict what happens in there. But the basic idea is that the baryon settles on a rotationally supported disk where they form stars and do other things. A prediction of the theory in particular is that the distribution function of the specific angular momentum and the size of the disk, which is proportional to the specific angular momentum, is a log normal function. So the question is, do we see these general features? It's a very general prediction, right? Do we see these general features in the disk? Get at least the fundamental features of the theory of how baryons accrete on dark matter halo right. But at high redshift, we also know that very often we encounter galaxies that are very compact, with very high stellar density, or at least we think the stellar density is very high. Certainly are very compact. In fact, a redshift larger than roughly 1.5, all passive, a big fraction, the majority of passive massive galaxies or low star formation galaxies are nearly all compact. Okay? So they should be the first system to passivize. And there are comparable numbers of similar star-forming galaxies. Comparable means of the same order of magnitude. Maybe it could be a third less or half less, but similar number of compact and massive star-forming galaxies. Are they also disks, in particular compact disks? Somebody actually suggested this, Van der Velde and collaborators.
A little overview of what's going to be the program tomorrow morning, and he's going to talk about UV morphology of star-forming galaxies at redshift 6.
So at least from the observational viewpoint. So it's been said already, it will be debated much more tomorrow, but our general ideas about how baryons populate dark matter halos and then settle there and form stars is basically, I don't know what's going on here. What goes under the name of the tidal torque theory. This nice cartoon comes from a recent paper by Mark Danovich and Avishai's group, in which is the idea is put down that the baryons enters, acquires redshift bins. They reach out all the way to redshift 6, even higher than 6, in fact. But redshift higher than 6, the statistics is spottier, of course. And what they find is they do find, there's also they do find, for example, that the average evolution is what is expected from the tidal torque theories in the case of mass-selected halos or rotational velocity selected halos. We can't select by mass or by rotational velocity, so the selection is somewhere in between. But the data fit nicely, are bracketed by these two cases. They also do find a key, one of the features of the theory, that the distribution function of sizes in the various redshift bins is something that strongly resembles a log normal theory, which would suggest that we more or less data. I'd like to point out this recent and quite nice work by a team of Japanese led by Shibuya. Paper is now published on APJ supplement. And these guys have studied just shy of 200,000 galaxies from the whole Hubble archive. They have selected star-forming galaxies in various ways, but at high redshifts, a redshift larger than about 2, primarily as Lyman Bray galaxies from the UV colors, various flavors of selection. And they've measured their morphological parameters. And what they find here is a measure of the average RE, half-life radius of the Sursich function, the Sursich index with their dispersion, and also the projected density of star formations in various